Hi, it's nice to have you here on today's Living Labs webinar. I hope that all of you can hear me well. If there are any issues, please let me know in the chat window. Okay, I think that there are no issues with you hearing me, so we will begin today's webinar. So you can see today's agenda. First, we will discuss the AM, so additive manufacturing production process in general, and we will be solving a production task. You may say doing a kind of case study altogether. That will be later verified in real life on a real production line on following event, which is called Model Factory, which will be held in facility of our partner Materialise. But more on that will be said later on. So my name is Gustav Koenig. I'm a specialist in additive manufacturing. I gained my experience in private company, and now I'm associated with Wrocław University of Science and Technology. And this webinar was prepared by Michał Olejarczyk and Piotr Gruber. So before we begin with our webinar, I would like to run a little questionnaire, a poll, and I would like you to answer some questions in the meantime. And after everybody answers, we will have a little summary of your answers. Okay, I can see that you are answering the questions. Thank you very much. And in the while, I will close the poll. In the meantime, I would like to tell you a little bit about the task that we will be discussing today. So the task that we will be discussing today is a sort of manufacturing problem that you may experience in your company while incorporating additive manufacturing in your processes. And we will try to analyze a sort of case study about producing a part that can be very customizable and very varying in production. Okay, I will now close the poll and I will launch another question regarding your experience in additive manufacturing. So here are the results about the later poll. I can see that only few of you had completed our previous webinars, but that's okay. We will have a little review of the basic information. Okay, the second question is about your experience with additive manufacturing. So I will also give you a little bit of time to answer that question. Okay, thank you very much for answering the poll. So I can see that majority of you have some general knowledge about additive manufacturing, and some of you have even advanced knowledge about additive, which I am glad to hear. Okay, back to the topic of today's webinar. So as I explained earlier, we will try to solve a sort of case study together, and I'm hoping that this will give you a little bit in-depth knowledge about designing the production process involving additive manufacturing. I hope that this will help you incorporate additive in your own company. So to make this a little bit easier and more engaging for you, I thought of a product that can be familiar for everybody. And as an example, I pick up a phone holder. And as you probably know, the whole process starts with some kind of concept, an idea of a product, which then is turned into a drawing. And this is still more in an artistic area, but then engineers have to get involved in the process and create the computer-aided design of the part. And this is the very early stage, but this stage is very important for any type of production, especially for additive, because we are going to produce a part directly from our CAD design. So every decision you make on the design stage is crucial for the production, for the economical aspects, and for part quality as well. The later step, of course, is production, and here you have to involve your production knowledge and know-how, specialized technologies that are available to you, and your experience. And we'll try to go through these steps and these processes to show you how to easily incorporate additive. You can incorporate additive within your existing business model of your company, but you can also create new business models based on additive. especially where the product has to be highly customizable by the customer. In our case, one of these business models that we thought of is a sort of web-based cloud application that allows customer to interact with the product, design and change the product according to his liking. This data could be saved and processed within the cloud and next uploaded directly to your production plant. This is a thing that is possible, especially for additive manufacturing. So as I said, we will do a quick review of additive manufacturing process, the steps, and make a little reminder for less experienced attendees. So in general, the additive manufacturing process, as I said, begins with a 3D computer design, a 3D model, which can be designed either within a CAD software, but also we can use software intended for computer graphics, and reverse engineering can also be a good source of a 3D model, so we can use a 3D scanning. But also there are a lot of online repositories, libraries of finished 3D models that we can use free of charge, or maybe buy a specific model online. After we acquire the 3D model, it is very important to convert the file format for additive. Currently, the most used file format is STL, which does a tessellation of the CAD body, so you get a triangulated mesh, a sort of approximation of CAD model. After preparing a file for additive, the first step regarding the production process or pre-production is to prepare the design within slicing software, which converts the 3D body into slices that will later be reproduced by machine in layer by layer manner. In the manufacturing step, you have to provide to the machine the data for the process, so any parameters connected to the specific technology and specific material that you will be using. Also, very important step after the part has been built is the finishing step, which often is neglected, and it is very worthwhile to get a little bit more knowledgeable about finishing processes that are available for 3D printed parts. So within that process, we will today focus on powder bed fusion technologies, and the choice for powder bed fusion technologies was made based on their capabilities to run a high volume real life production. So in terms of these technologies, we are moving away from low volume and prototyping applications, and we are going towards high volume customized production. Within powder bed fusion technologies, we have two specific processes. One is selective laser sintering, and the second one is multi-jet fusion. The selective laser sintering, short SLS, uses laser to melt polymeric material, where in multi-jet fusion, we use fusion agents to fuse the whole layer with light source. Going more in depth with the processes, I would like to start with selective laser sintering and show you a little video that explains the process and the key steps behind selective laser sintering.
Here's how the selective laser sintering process works. The process chamber of the machine, along with the powder container and working platform, are first heated to a temperature which is just below the polymer melting point. When the temperature is achieved, the recoater spreads a thin layer of powder on the working platform. Then, the CO2 laser beam scans the powder surface and selectively melts the polymer particles, which causes the powder to bond. The movement of the laser beam on the material surface reproduces an entire cross-section of the part to make a solid. When the layer is finished, the build platform moves down, and the recoater applies a new layer of powder. The process is repeated until the whole part is completed. After printing, the parts are enclosed in the loose powder. The powder container must cool down before the parts are unpacked. This can take as much time as the printing process itself. The final step before recycling the powder is to clean the parts with compressed air or by sandblasting.
Okay, as you can see, the selective laser sintering process is fairly simple. The same case is for multi-jet fusion. And here I would like also to show you a little explanatory video.
Here's how the multi-jet fusion process works. At first, a layer of powder is spread on the build platform, where it is heated to just below the melting point of the polymer. The printhead then sprays the fusing agent over a section of the part. The task of the fusing agent is to facilitate the sintering of the powder. At the same time, a detailing agent is sprayed near the outer edge of the part, which hinders sintering, thus improving geometrical accuracy. In the next stage, a high-power IR heat source passes over the build platform and combines the powder in the area where the fusing agent was applied, leaving the rest of the powder unchanged. This process is repeated until the part is finished. After printing, parts are enclosed in a loosely bonded powder within the container. The powder container is transferred to an external cooling station. As a result, cooling time is shorter and the printer can start another process immediately. The final step is cleaning the parts in a specially adapted cleaning station.
So I hope these videos reminded you a little bit about those technologies, and the main differences between those two are very little, I would say. If we would go in depth in comparing those technologies, we can say that the multi-jet fusion has slightly higher efficiency, and in terms of accuracy, SLS will be only slightly better, but certainly within SLS technology you have wider range of materials available. The biggest difference between those two technologies is that for SLS, the parts after the process have the same color as the color of the powder that was used, which for nylon is white. That is a kind of advantage because later in finishing you can easily use dyeing process to apply selected color for the part. On the other hand, for multi-jet fusion, the part is colored during the process by fusing agent and is typically black or dark. You can also use a couple of fusing agents to print multicolored part. But in summary, both of these technologies are very similar. Okay, that would conclude our AM technologies overview. So this recap session for our previous webinar. I hope that all of you are familiar with the technologies at this stage. And now I would like to move on to our case and our task that we will be solving during this webinar. So back to our product, our phone holder. So based on this example of phone holder, we would like to present to you a sort of approach for preparing a production involving additive manufacturing. And the first step in process of incorporating additive within your company would be to do a sort of design evaluation for the product that you are planning on producing using additive. This evaluation procedure is not a universal approach. I'm well aware of that each of the industries has to have its specific approach, but this evaluation that we are showing you today is a good starting point for any business and any industry involving any business model. So to start, we have to define the evaluation parameters. So the key parameters of our product that we will be focusing on during the evaluation. I highly encourage you to focus on technical data first and on the process and product parameters that can be measured, so measurable parameters. This can be connected with the geometry of the part, but also with a analysis results using finite element method or any other analysis that you running within your company for your products. Also measurements and physical test results would be good parameter for the analysis. You have to also decide whether some of these parameters that you specified are more important than others. And if that is the case, you can assign weights to a certain parameters to indicate that they are more important than the others. Also, it is important to set a uniform scaling and scoring for each parameter to calculate the overall average score easily. So you can map, for example, the test results for each individual design to a specific scale of your evaluation process. And the last step, of course, will be calculating the average score. So let me magnify a little bit this our table with the evaluation of our form holder. As you can see, we focused on following parameters. Minimal build height. So the minimal height of three parts dimensions, either in X, Y, or Z direction, that can be used to build a part depending on the part orientation. Also, the amount of space that part occupies, which we call a bounding box volume, is very important. So basically, we multiply all the maximum dimensions of the part, and we get the bounding box volume. The part volume itself will tell us how much of material will be used during the process. So this is also a good parameter to incorporate in our evaluation. Part built space usage can be calculated as a fraction of part volume within the bounding box volume. So how much of this bounding box volume is actually occupied by the part. This will be later shown during the process preparation stage. You will understand how this can affect the whole process and the economical aspect of additive manufacturing. The part area can also be a good parameter because you can use this, for example, for calculating the cost for finishing processes. For example, painting or dyeing, usually the price of these processes are based on the part area. Wall thickness is one of the technical parameters that can be crucial for the build process itself and can even make the process unable to complete because of build errors, and also affects the part quality in a very substantial way. As for parameters which are strictly connected with our design, we can, for example, focus on the stability of the phone holder. This would be a crucial parameter for the customer, the end user, and also we can focus on durability and the functionalities that our product is offering. In some cases, with certain design, we can do a little bit more. And if we simplify the design, we are taking away some functionality, but maybe we can make the part cheaper. So this is also a good parameter to take into account. Of course, the number of parts will greatly affect the final result in terms of the process itself, because we would have to have some kind of assembly steps, but also in terms of the costs. So as you can see, we ran this evaluation for a couple of designs of a phone holder, starting from a very simple one, classic designs. We increased the complexity and modified the design to a certain degree within very similar examples. So you have this classic series. The last example is more personalized, and the last two examples, to be specific, are more personalized because they offer you to have a writing on them directly, which can be additional advantage for the customer. But we can also evaluate more advanced designs, for example, designs more suited for additive. So you can have a design that you are able to fold into a flat sheet with a credit card format. This uses a designed feature used also in injection molding, which is called living hinge. And you can also have a folding design that is built from two parts within the same process. You can also have a very minimalistic approach to the design and build a very compact phone holder, but certainly you'll have some issues with the stability. But as you can see, if the part is smaller and if the minimal height is lower, in general, within additive manufacturing, it will be more preferable. So as you can see from this analysis, we have a couple of designs that we can pick that are equally scored by the average. And in our case, we went with the classic design 6, and which can be seen here. In case of this design, it has the best customer key parameters, so stability, durability, functionality, and sufficient technological parameters affecting part quality, like wall thickness. The wall thickness is rather uniform across this design, which will ensure the quality. And also, it has sufficient technological parameter affecting part cost, like build height, volume, and build space usage. In terms of the design itself, and in terms of evaluating the design one of the important things is to take into consideration the design guidelines for a specific technology. So in case of selective laser sintering, you can here see a list of the important selected by us parameters that will affect part quality and the build process itself. So one of the key parameters, as you know, is the wall thickness, which for selective laser sintering and multi-jet fusion has to be at least 1 millimeter and should be uniform across the whole part. If possible, also you have to ensure that for additive, your holes are big enough to be able to be produced by the machine. If you have smaller holes, they can easily collapse and you would have to remanufacture this type of features. Okay. So this is only a couple of example design guidelines, but there are a lot more, and you can download a handout through the GoToWebinar panel, and you'll find a lot more there. So for those of you that would like to try to design a customized phone holder for themselves, we've prepared a parametric customizable model within open source software that you can use, and I will give you a quick demonstration of this process and discuss the parameters that you can modify within such a design. So this software is downloadable through the package of learning materials that were sent to you earlier on. So within the OpenSCAD software, you can open the design that we provided by going to File, Open, and selecting Phone Stand as CAD file. By hitting Open, the design will be shown in the viewing area of our software. And as you can see, this is our classic design that has a couple of neat features. It allows you to place the phone and then plug in the charger through a hole and from the below. And also, as you can see, we can incorporate some text on the base. So you don't have to focus on the things that are going on the left side, so you can simply close that. But on the right side of the screen, you will have a customizer that allows you to customize the design. So as I said earlier, we are focusing on customized production in this case. Going to the STL file that we'll be saving by the end of working with this software, one of the most important things with file format for additive manufacturing is the resolution of the STL file. So if you zoom in very quickly on this preview, you can see that this curvature here, this corner rounding, is approximated by a flat faces Each of these flat face is composed of triangles. So as you change the resolution, you can notice that these flat surfaces become bigger, and this can affect the final quality of the surface on our part. So it is very important that when using your 3D software, when exporting to STL format, that you adjust the resolution just right. Let me demonstrate you what is the difference if I decrease the quality. As you can see now, the surface is approximated by only 4 faces, which would result in terrible quality of our end parts. On the other hand, when I go back to the maximum resolution, the surface will appear smooth on the finished product. In case of our phone holder, you can customize it according to your phone width. You can customize the height. So let's say that my phone width is 80 millimeters. As you can see in the viewing area, the model updated automatically. The same goes for height. I can use either the slider or the input field to decrease or increase the height. I can change the wall thickness according to my liking and according to expected maybe durability. I can also change the cable hole diameter here, for example, to 25 millimeters if I have a larger charging adapter. And I can also position the hole up and down. So these are the very basic parameters to customize, but I hope that they give you an idea of a customization that you can provide to a customer in certain business models incorporating additive. Here, additionally, you can change the writing on the base according to your liking. For example, I can put my name in the second line here. And as you can see, my name is displayed here. Let's say that I would like to also have this part printed in a specific color. So in this case, I have a couple of options to choose from, and this will be manufacturing using powder bed fusion technologies, and in finishing step we will be able to change the color of the part according to these options. Let's say I would like to have the part orange. When I'm satisfied with my design within this OpenSCAD software, I have to go to design, render. This will create a solid model that I am able to save to my STL format. As you can see, the part is now rendered and I can view it a little bit more easily because in the preview mode I have had some overlappings here that program does not render very well, but now I can rotate and have a look at my final design. What's left is to save this design to STL format. I will do this by selecting F7 key on my keyboard, which is export STL file, and I can save this to my drive. This file can later be used directly in the build preparation step. So if you would like to create your own customized version of the phone stand, you can use the software that we provided, and we also created for you a simple instructions for using this software, which is also available within the handouts to download. So let's move on to the process preparation stage. In this stage, one of the first key decisions that you have to make is that you have to select the build orientation. This will greatly affect the economics of the process, so the part cost, but in terms of additive, this will also affect the quality of the part in terms of mechanical properties, as well as some geometrical properties like accuracy and surface quality. As you can see here, we've done a comparison of two examples. So we've compared a upright position and on lying down position, here noted as XYZ and ZYX highlighted on the right side. When we are discussing those two very different orientations, what we will notice if we analyze the mechanical properties is that the elastic modulus is fairly the same. We'll experience a little loss around 15% with tensile strength, and the highest loss will be in elongation at break, which can cause fracture in load-carrying parts. But in this design, this is a non-load-carrying parts in terms of and the weight of the phone is fairly low compared to the mechanical properties of our material. So we can easily go with the most efficient way and most economic way, in this case, the XYZ direction. The second step during the production process is nesting. And nesting, by definition, is a way that the parts are made in one build cycle and are located such that their arbitrary oriented minimum bounding boxes will overlap. So as you can see in the picture, the parts overlap each other sort of in interlocking, maybe not interlocking, but intercepting positions. This can be shown on a video that I will play now. So as you can see, for the nesting process, we use specialized software, which is often delivered by the machine manufacturer, but there are a couple of machine independent solutions that you can use. And this software usually allows you to analyze the part in terms of the geometry and STL file format, and also allows you to do the nesting process, so lay down the parts within the build volume of the part to minimize the build height. So here you can see a couple of examples of nested build platforms with our phone holder design. In this comparison, we used a fairly large phone holder, maybe even that could be used for a tablet. So we called it a tablet-sized phone holder. So in this case, we are comparing three different machines with three different build volumes that are listed next to the pictures at the top. And in the table, you can see the number of parts that can be built on each different machine and the corresponding build height. So on the smallest machine, you can build only like around 18 parts, while on the biggest machine, you will be able to produce 126 parts. In terms of cost per part, on the smallest machine, we have a price of around 80 euros, which will decrease for the larger machines. One important fact here is the price presented here was calculated based on one of the service bureaus, Materialise to be precise, and these prices are the customer prices, so these are not production costs for a piece. Of course, the price will change not only due to machine used and the number of parts that are built, but rather the more affecting parameter would be the dimensions of the part itself. So here you can see the comparison between a small, medium, and the large design and the prices for each one. So if we decrease the size and decrease the build bounding box of each part, the price can be considerably lower. As you can see in the graph, the relationship between the dimension and the cost is almost exponential. Part finishing. Part finishing is one of the most neglected steps in incorporating additive within your production processes, and you can certainly take advantage of available finishing options. So typically when you run a production, maybe you order a part that is 3D printed, you receive a normal finishing, which would involve in powder bed fusion technologies to remove the loose powder and doing sandblasting using glass beads typically. And what you can additionally do to your parts is that you can use a sealing finishing, for example, where you have to have a watertight part or airtight part. You can also do the smoothing process. And the smoothing process is very interesting in terms of powder bed fusion technologies, because usually you will have a part with fairly rough surface. Parts are smoothed mechanically by polishing and using tumbler that vibrates at high frequencies. The smoothing with this technique only allows you to do the smoothing on the A side of the part, so the outside of your part. What you have to take into the consideration when using smoothing on your parts is to avoid thin walls, because during this mechanical process they can wear or damaged. Finishing allowance is recommended for this type of finishing process, and typically this is around 100 microns, so 0.1 millimeter. And you have to be aware of that. Using polishing on your parts will affect the edges of the part, which will be all rounded, so the part will be not as crisp as with normal finishing. The process is typically limited to a range of part sizes from 30 up to 200 millimeters. Another very interesting finishing process is color dyeing, which allows you to color your part on one of the basic colors. And typically you have a limited amount of colors with this solution, but this solution is fairly cheap. Dyeing is a process where the part is submerged in a bath containing coloring agent like a pigment. And you can also combine those finishing processes. Typically, you would just smooth the part first and then apply dyeing. Instead of dyeing, you can also do the painting, which will allow you to color the part on both sides and on internal features even sometimes. But this is fairly expensive process, as you can see, this will increase the lead time significantly. So this would conclude our process preparation part of the webinar, and I encourage you to post some questions that may have arisen during the webinar. So I can see that there are two questions, I believe. One regarding the software that was used for the nesting process. As I said, typically this software can be delivered by a machine manufacturer, but there are a couple of solutions that are widely available. one of them is a Materialise Magics, for example. This is a fairly expensive solution, but certainly one of the best on the market. And you can also use NetFab software by Autodesk, and there are a lot of more options that are less expensive. The other question was about the price differences between selective laser sintering and multi-jet fusion technologies. So in my presentation, I believe that for the large form holder, the price was 84 euros. Why this was the price for selective laser sintering technology, while for multi-jet fusion, the price would be a little bit lower, around 74 euros. So 10 euros in difference. As I said, the difference is small. But you have to bear in mind that the parts produced with multi-jet fusion will have a dark color. So in terms of this part, for example, finishing using dyeing process will not be possible. So the other question is the printing time calculated along with nesting? If yes, how? So if you are using proprietary software from the machine manufacturer, the machine manufacturer will simulate the process within the software with actual machine parameters. And for advanced software, not from the machine manufacturer, this is also the case. So for Materialise Magics or for Autodesk NetFab, they have a built-in library of machines with the process parameters for each machine and material, which allows to calculate the build time very precisely. Of course, the time can be a little bit different from the one that you achieve on the actual machine. Because this is only a simulation, so a sort of estimation, but the difference in general should not exceed certain threshold. I would say this is around 10% of error that you will have in the estimation. So I think that this concludes the Q&A session. And if you have any more questions regarding powder bed fusion technologies, in the upcoming week, we will have a session with experts regarding both selective laser sintering and multi-jet fusion technologies. So our first expert that you can get in contact with is Piotr Zimniak from AAM Experience, and he is a renowned specialist in selective laser sintering technologies and additive manufacturing in general. You can contact Mr. Piotr on 28th January between 10 and 11 a.m. Central European Time, and on 30th of January in the same hours. If you have any questions regarding multi-jet fusion technology, second, our expert, Mr. Krzysztof Nowak from 3D Center company, a Polish division, will be happy to answer your questions on 29th of January between 10 and 11 a.m. Central European Time, and again on 30th of January at same hours. You can contact those experts with the contact information provided. This will also be sent in the follow-up email after finishing today's webinar. I also invite you to participate in our upcoming event, which is called Model Factory, which will be held in our partner Materialise production plant located in near Wrocław in Poland. This will be a study visit, which is very interesting because you can use our parametric software design to design your own phone holder, and it will be produced for you during this model factory study visit, and you will receive a phone holder of your own at the event. The event will take place at 5th of next month, and the deadline of registration for the event would be 30th of January. Please use the form, and that will also be sent to you by email on the end of our webinar. If you want to submit your design and maybe discuss this design during the Model Factory and have it produced, you can send your design by the 27th of January using Dropbox account directly to me. You don't have to be registered with the Dropbox to send your design. This information will also be sent to you by email. So thank you very much for today's attendance, and I hope that we will meet during our upcoming event. Thank you very much. Goodbye.